If Chapter 4 is coming in your exam, don't skip this video. This one revision could save you several marks.
Welcome to Teaching Science. Have you ever wondered why, out of all the elements in the periodic table, only one gets an entire chapter dedicated to it in your Class 10 chemistry syllabus? Well, today we are diving into what is honestly the most fascinating and sometimes the most misunderstood topic of the year: carbon and its compounds. I know this chapter can feel a little intimidating at first, but don't worry. We are going to break it down step by step in the absolute simplest way possible. Seriously, think about this for a second. We don't have a whole chapter just for nitrogen or oxygen, but carbon, an element that makes up a tiny, almost invisible 0.02% of the Earth's crust and just 0.03% of the atmosphere as carbon dioxide, it gets the spotlight. Why does this one mystery element basically dictate everything about life on Earth? Let's find out together. Here is our quick roadmap for today's explainer. 1. Why carbon is special. 2. Covalent bonds. 3. Carbon's versatile nature. 4. Homologous series. And 5. Chemical properties. Section 1. Why is carbon special? Let's look at this versatile element. Okay, major board alert right here. Despite its super low percentage in the Earth's crust, carbon is literally the foundation of everything around us. Your food, your clothes, plastics, medicines, even your own body, they are all carbon-based. And the reason why comes down to its exact atomic profile. Carbon is a nonmetal. Its atomic number is 6, meaning it has 6 electrons total. If we distribute those, 2 go in the first shell and 4 go in the outermost shell. That gives it an electronic configuration of 2, 4. Now, because it has 4 electrons sitting in that outermost shell, its valency is 4. We call this tetravalency. And this tetravalency is the entire secret behind why carbon behaves the way it does. Moving on to Section 2, sharing electrons, or covalent bonds. So, every atom out there just wants to be stable, right? They all want 8 electrons in their outermost shell. That's the famous octet rule. But carbon only has 4. Gaining 4 or losing 4 takes way too much energy. So what does it do? It uses teamwork. And this brings us to a crucial definition. A covalent bond is a chemical bond formed by the mutual sharing of electrons between 2 atoms so both achieve a completely filled outermost shell. It's kind of like 2 students who forgot their textbooks on the day of a strict classroom inspection. Neither wants to get in trouble, right? So they push their desks together and mutually share one textbook. The teacher walks by, both look like they have a book, and both survive. That is mutual sharing in a nutshell. Let's actually visualize this step by step with an oxygen molecule, O2. We start with 2 oxygen atoms. Oxygen has an atomic number of 8, so its configuration is 2, 6. Each atom has 6 outer electrons, which means they each desperately need 2 more to hit that magic number 8. Instead of fighting over them, they agree to share. They each put 2 electrons right in the middle. Imagine drawing overlapping circles around them to loop those shared electrons together. Because they're sharing 2 pairs of electrons, they successfully form a double covalent bond, which we write as O double bond O. Super simple, right? Exam tip time. Pay very close attention to this because it's a huge common mistake. If the board asks you why covalent compounds are generally poor conductors of electricity, do not just say because they share electrons. The examiners are looking for a very specific phrase. You must explicitly write that it is due to the absence of ions. See, because the electrons are totally locked up in those shared bonds, there are no free charged particles, no free ions, floating around to carry an electric current. Write absence of ions, and you will secure those marks for sure. Section 3. Carbon's versatile nature. Focusing on catenation and allotropes. Did you know carbon can form literally millions of different compounds? The number of carbon compounds outnumbers all the compounds formed by every other element combined. No way, right? Well, the secret is a superpower called catenation. This perfectly shows off carbon's super-friendly nature. Catenation is the unique ability of carbon to form stable covalent bonds with other carbon atoms. It can build long straight chains, branch chains, or even these complex circular rings. When you combine this catenation superpower with its tetravalency, its ability to bond with 4 things at once, carbon becomes practically chemically unstoppable. Now, depending on exactly how carbon bonds with itself, it creates completely different materials. We call these allotropes. Take a look at graphite. Here, each carbon atom bonds to just 3 others in these flat hexagonal layers that can literally slide right over one another. That's exactly why the graphite in your pencil lead is so soft. But If you take those exact same carbon atoms and have each one bond tightly to 4 others in a rigid 3D framework, you get diamond, the hardest natural substance on Earth. Same exact element, entirely different personalities, just because of the structure. Section 4. Homologous series and groups, basically the carbon families. With millions of carbon compounds out there, it would be pure chaos if we didn't organize them. So chemists organize them logically into families to keep things easy. But to name them, you need to know the secret code, this prefix list. You absolutely have to memorize this. Without it, IUPAC naming is just impossible. 1 carbon is meth, 2 is eth, 3 is prop, 4 is bute, 5 is pent, and 6 is hex. So if you spot a single bonded chain with 3 carbons, that's propane. 4 carbons, butane. Go ahead and pause this if you need to, and just lock these into your memory right now. Once you've got those names down, you can group them into a homologous series. This definition is a huge board exam favorite, so listen closely. A homologous series is a family of compounds that have the exact same chemical properties because they share the same functional group. But here's the catch. As you go down the family line, each successive member just adds 1 carbon and 2 hydrogens, a CH2 unit. Because a single CH2 unit have a mass of 14U, the molecular mass of the compound increases by exactly 14U every single time you move down the list. And as it gets heavier, its physical properties, like boiling and melting points, smoothly increase right along with it. So I mentioned functional groups just now, but what does that actually mean? Well, if you replace just 1 hydrogen atom on a carbon chain with a specific group of atoms, you completely change that compound's whole personality. For instance, slapping an OH group onto a simple gas suddenly turns it into an alcohol. Adding a ketone or a carboxylic acid group gives the molecule an entirely new set of chemical reactions. These are your functional groups, and they are the absolute bosses when it comes to dictating how a carbon compound is going to behave. Section 5. The chemical properties of carbon, starting with combustion. We rely on carbon-based compounds every single day for fuel. Think about the LPG used for cooking, or the petrol in cars. When carbon or its compounds undergo standard combustion, which is really just a fancy way of saying an oxidation reaction in the presence of oxygen, they produce carbon dioxide and a massive amount of heat and light. Whether you are burning pure carbon, methane, or ethanol, the end products are largely the same. And here's a quick exam tip for you. Always, always balance these equations on your answer sheet exactly like we practiced back in Chapter 1. I want to pull out this specific quote straight from an NCERT exercise because they love using this as a multiple choice question on the boards. While cooking, if the bottom of the vessel is getting blackened on the outside, it means, can you guess it? It means the fuel is not burning completely. That black soot you see, those are unburnt carbon particles. It basically tells us that the air supply to the flame is blocked somehow, which causes incomplete combustion and that messy, sooty flame. All right, let's do a rapid-fire 1-minute chapter revision to really lock these high-yield concepts into your brain. Number 1. Carbon achieves stability by mutual sharing, forming covalent bonds. Number 2. Covalent compounds are poor electrical conductors because there are no free ions. Number 3. Carbon's unbelievable versatility comes from its tetravalency and its catenation superpower. And finally, members of a homologous series always differ from their immediate neighbors by exactly 1 CH2 unit. We have covered a lot of the core foundation of carbon today, but I want to leave you with one last really cool thought. We know carbon forms these brilliant covalent bonds to survive, and we know it builds our fuels. But what exactly happens when carbon teams up with specific molecules to create the soaps and detergents we use to scrub dirt and oil off our clothes every single day? That almost magical process is called saponification, and I highly encourage you to dive into that as you continue your self-study. If you found this explainer helpful, please like, share, and subscribe to Teaching Science. And definitely don't forget to press that bell icon so you never miss our next CBSE Science lesson. Keep up the great work, happy studying, and I will see you in the next one.